why she keeps coming, because she knows everything about it already.
But she's always supporting us.
Yes. Yes.
Hello, Angelica.
Hello, everyone. How are you?
Hello.
Welcome,
Fine,
Angelica.
thanks.
So today we talk about how to make toys for ourselves. Of course. If anybody was here 2 weeks ago, they probably know how to create 3D models. And I will quickly go over this today also. But if you're interested in how to create 3D models, it's heavily recommended to watch the video from back then, or go over the GeoGebra book that was created, or just, I don't know, walk through the entire presentation again is probably good. And if you have any questions of any kind, you also can always email Ceci or me or Angelica, who is already a pro, can also give you answers. Yeah, and so today we are going to talk about 3D printing. So that's the production part of the entire thing. We have a GeoGebra book again, and I will give you the link to the GeoGebra book with lots of links and information into the chat. Classes be scheduled to teach GeoGebra? I don't understand. I'm not sure what you would like to know.
Mm-hmm.
I just made a GeoGebra book so everybody can read up on the information and talk about things or share things or something. So you want a class about GeoGebra? Is that what I understand that we could do? I think the GeoGebra team does that a lot. And GeoGebra is very useful. So for sharing resources, that's what I use usually. Okay, but what I'm going to talk about today is what 3D printing actually is. So what does 3D, so why not carving into woods or something? Benefits and drawbacks of 3D printing. So which technologies have which benefits, where to get appropriate models from. Like I said, briefly going into what makes a 3D printable model, what are software needs, and which software is needed to go from a model or the idea to the actual print, because that can get quite complicated. Then behind Ceci, we have a printer, and I also have a printer here, which we created. And if we have time, questions, and if we don't have time, there she has it. If you can see, Ceci, we got 2 versions, 3 different printers, no, 4 different printers in her back. And I think they are from 3 different manufacturers. So as you can already see, they come in lots of sorts and sizes and variations. And to guide you through all of this, I will help you with this course, hopefully. So what is 3D printing? What does that actually mean? 3D printing is creating an object out of a digital file. So first we must have a digital file describing a 3D object. And then we can give this file in some version to a machine, and a machine can produce this. And it's called additive manufacturing also, because the difference between 3D printing and other manufacturing versions is you add material layer by layer. So it's kind of like, if you would compare it to arts, it's creating a plastics, like where you add things, versus creating a sculpture where you sculpt out things. until you have your item. So that's the large problem. That's the large difference between them. And as you can see on the picture on the upper right, this is one of the variations that's very common, and I would recommend for schools. You just have kind of a plastic that you melt, and then you add it layer by layer by layer. So basically, by making that kind of adding layer by layer by layer, you create a two-dimensional problem out of a three-dimensional problem, which makes it much, much, much easier. And there's some benefits that you have by creating something like this. So by having the possibility to add it layer by layer, you can create objects within objects, as you see on the lower right. You can create interlocked objects. That's something that you really, really, really rarely can do with other, I don't know, production possibilities. So for example, for industry, this can be extremely valuable because imagine you would produce lots of parts of, for example, a fan. Let's talk about a fan that's just blowing your hair dry. And they got lots of parts and pieces inside. And if you create all of them separately, you have to assemble them. Whereas if you can create them in one step, you do not have to assemble them. And you do not even have to open the object. So you can make it in there, create the object in there, which can save enormous money, enormous masses of money, because you can save up on time. And for educational purposes, it's also very useful because, for example, another thing that additive manufacturing can do is it can be very, very personalized. So does anybody have an idea what the absolute killer application currently is for 3D printing? So where 3D printing is used more than other technologies? Anybody has an idea? What could be the most personal thing that you could think of? As personal as fingerprint. If nobody has an idea, I will tell you, because what currently is the absolute killer application of 3D printing is earpieces to help listen, because humans have ears and every ear is completely unique. So every person has completely unique ears. And that in turn means if you have a listening aid, then you can produce it by 3D printing to fit it exactly to your ear. And this is what the current situation is with 3D printing. So most listening aids are created by 3D printers. Okay, 3D printing is extremely old, just as old as I am about. About 40 years ago, the first 3D printing technology. So there's a couple of technologies, and I will get to that in a minute. But the first 3D printing technology was stereolithography. And it's really, really, really old. And there's discussions who has the patents on what and who really, really invented it. But I think the current company holding the patent is 3D Systems. And imagine how old this company is, that it still has the patent on something. So 3D printing companies last for very long, usually, if they kind of have a large enough mass. Some of them vanish again if they produce printers, but the ones that create technologies, they kind of remain. Later, FDM, or fused deposition modeling, was invented by Stratasys. That company also still exists. And the entire reason why this 40-year-old technology is getting to schools now only. So maybe you didn't know, but in industry, it's been used for ages and ages, for decades. But in education, it was not. And the reason was because of patents. 3D Systems and Stratasys had patents on SLA and FDM. And in 2012, as far as I remember, the patent for FDM fell. And many mathematicians actually came together and decided, okay, this is a really, really cool technology. Let's make it open source. Let's make printers that can be used by anybody. Let's make it widely available for everybody, because it can be really, really useful, maybe also for your home. If you want to make some present, some personalized present for something, that could be what you want for your home. And previously, 3D printers cost really, really an enormous amount of money. So for example, an FDM printer from Stratasys, they are still very expensive, but they were, I think, about 50,000 euros one. Whereas, Ceci, do you know the most expensive printer in your bag?
No, but I will check with the techniques.
So I think the white one, the smaller white one, that's 1,500, and that's an expensive one. So you can get 3D printers, I think from 150, 200 euros upwards.
The most expensive are Craftpot, and it's 1,800 euros around.
Ah, thank you very much.
The more expensive.
Yes, but it's far from 50,000, and that's, I think currently FDM machines from Stratasys still cost 20,000, and they have regulations regarding the material, and they are very restrictive in what they can do. They're really, really good and reliable, but yeah, so that's about the difference. And this is how much less printers used to cost and started to cost. And if you have printers that you assemble yourself, they can get really, really cheap, like 200, 300 euros. So if you have somebody crafty nearby, you can get a 3D printer really cheap. And then there's also a third technology that I wanted to tell you about, which is selective laser sintering, which means you have a powder material, usually nylon, and by a laser, you kind of melt it together. Or you could use also metal powder, and with a laser, you could melt it together. So that can also be done in layers, and that also counts as a 3D printing technology. And then there are jetting 3D printing technologies. That's basically you have a really, really huge machine, and you spray a material somewhere by a large printer head. Companies that usually do 2D printers, so to speak, like, I don't know, Brother or something. So those ordinary printers, office printers that you have, they started creating this 3D printing technology also. And if you want a large comparison, in the presentation, you find a link where you can read up about what is what and how it works and what it looks like. So FDM is something very common, and probably you know this kind of layer-wise look. So this is what you're maybe most common to see, or most used to see. And then there's SLA, so laser sintering, which can be very, very smooth. So about the strengths and weaknesses, what you can see in this chart is the more filled a dot is with pink, the better it is. So we have FFF, FDM. That's something that I forgot to tell you. Stratasys still has a patent on FDM, but only on the name. So therefore, mathematicians invented a new name, which is fused filament fabrication, and therefore FFF. That's the reason why FDM and FFF it's basically the same thing, but that's the reason why in most areas that is not Stratasys, FFF is used. So FFF, that's the common printer that you have in the back of Ceci also. And as you can see, they use, as a material, they use thermoplastics, and they're very cost effective, as we just said. They are pretty easy to use, And the objects that you create from that, they are very durable. So they last for quite a long time, depending on, of course, what you actually create. The speed is really, really bad. So it's not very fast. That's something that you have to keep in mind whenever you use 3D printing in your class. And that's something that you will experience yourself also in this course. Stereolithography, so that's the first 3D printing technology, uses resins only. So resins, that's basically a liquid that solidifies if you kind of put light on it. Maybe if you're lucky like I am, you also had that with the dentist, is those plastic things that you get where they then put UV light on. So basically, more or less, that's quite similar. You also have a very low speed, and it's not very cost effective, but you have an extremely high precision. So the things that you do get from that, they break. And the next problem that you have is resins sometimes are cancerogenous, and you don't want to give your students cancer or get cancer yourself. So you really have to think whether this is a good idea for your school. Selective laser sintering has a very high precision, a very high speed. The things that you create with it are very durable. The machines are pretty costly, so they still are about 200,000 to 300,000 if you buy an industry, so like euros, 200,000 euros. If you buy an industry machine, there are machines you can use at home for, I think, about 10 to 15,000, but 10 to 15,000 is about still very much. They are extremely hard to use because they're extremely complicated machines. So it's probably not the best choice for your school either. And then you have the material jetting that I was talking about previously. It's also very high speed, very high precision. It is about cost effective. So the machines also cost about 250, 300,000. And as you use resins, the durability of the object is really not that good. So for example, you could make figurines that you put somewhere as a model to look at and never touch. So that's more or less what you can do. But they can use lots of different materials maybe also in combinations. But mainly it's resin, and resin just hardens and hardens. Okay. The materials, I was just talking about the materials. This is pretty much what we compare here. Thermoplastics, that's what we use with the FDM or FFF printers in the back of Cecilia. And this is the material that also is Legos is from. So you can imagine how durable the things are. Basically, if you have Legos that lasted for some decades, you can kind of assume that the things you make with your 3D printer in the way that Chelsea has in her bag also last for quite a while. Resins, you can create very, very delicate things with resins. On the right side, the gray figurines, they have a very high detail. They're really, really nice. But they can also easily break. So basically, resins are useful for what you see there, for small and very detailed figurines. And then you have the powder-based, so the sintering, where you have metal powder or nylon powder, the sintering things. With the bus, you can also see the layers. So it was sintered in layers. You can see that on the side of the bus. However, it's a powder-based thing. So basically, you dig out your objects out of the powder. So you put on powder, and then on some spots you put on a laser, and there it hardens, and the rest of the powder you have to take off, and it makes a huge mess. And that's one of the reasons why it's very complicated in school. So if you would have it at home, you would need additional machines like blow dryers and whatnot, and vacuum cleaners and stuff to remove all that material. Oops, yeah. And about materials, you also have more detail here if you want. Okay, but what we are going with is a thermoplast, and in our case, PLA. And unfortunately, this is in German because I usually do my courses in German. But basically, this is telling you that it is a biodegradable material out of cornstarch, usually. So I live in Styria, there's corn everywhere around me. So basically that would be material that I could use for 3D printing. It has quite a medium density. It is not really easily to burn, so it's not very flammable. But there's a so-called glass temperature, about 60 degrees to 70 degrees, which is the temperature where it kind of starts deforming. So that's already reached if you put an object into your windshield of your car. If it's a hot summer day and you put something made out of PLA into your windshield, behind the windshield in your car, then it very likely will deform or become a blob. It starts melting around 200 degrees, and that's also where we usually have the 3D print at. Yeah, it's highly UV sustainable, so usually it's not, it lasts quite a while, basically. What's also important to know is the material that we talk about, it's called filament. And it usually comes, I'm going to stop my presentation so you can see it better. It usually comes in rolls like this. So this is 1 kilogram of PLA. This is a glow-in-the-dark PLA. They come in a variety of colors, and you can have extras like glow-in-the-dark. It's a bit hygroscopic, so that's the reason why it's in plastic. So usually it's best to have it in a plastic or cover it somehow. And one of these spools cost about 20 euros, and they will last for a very, 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 very long time. So usually one of these spools probably should bring you over the course of half a year easily if you do projects. Okay, back to the presentation. Interesting is that if you have different colors, the colors that are added to PLA, as PLA is slightly yellowish, they can change the properties. So that's the reason why we have a melting temperature between 120 to 210. So depending on the color, it might work better or it needs higher temperature or something. So whenever you change material, if you don't find information on the material itself, you just probably have to try around a bit for the correct temperature. PLA is biodegradable, as I said previously, and it's basically cornstarch. The pros are it's very easy to print. It's food safe if you keep the printer clean. It's biodegradable to an extent, which I will explain. It comes in a lot of colors. It has a very low melting point. That can be a pro, but also usually is a con, because if you have it lying around behind a window and the sun's coming, then it probably is not keeping the form as it should. It's not as strong as other materials. And if you want to reuse it, you will have to divide up the colors, but they come in a very large variety of colors. So how will you divide all the rests that you have? For PLA production, I was talking about the corn outside. You need about 2.5 times more corn than you need for material. So the spool that I was showing you, that's quite a bunch of corn that I'm having in my hand. And that's also a problem, because imagine we would use plastics only out of cornstarch. But corn is also eaten by humans and fed to animals. So what happens if we make all the plastic out of cornstarch? We would probably run into problems. It would get more expensive. Then people probably would not be able to afford it for food anymore, or it could not be fed to animals, or animals would get more expensive. So if you have the idea now, hey, why not just make biodegradable plastics out of cornstarch, when the only limitation is it's getting soft at 60 degrees. There's problems with that. So think about these problems. And what does biodegradable even mean here? So biodegradable means if you put it into not a compost like this, you can put it to a compost, but it will take a long time. But if you put it into an industry compost, it takes up a few days to a couple of months, and then it's soil again. So that means basically this spool of material can turn into tomatoes in a couple of years if you wanted it to. If you would keep it uncolored, and if you would keep it clean, and if you would put it into an industry compost. If you just throw it into the wild, more or less, then it takes about 80 years to biodegrade, which is still super quick because PET bottles, for example, they take 450 years to biodegrade. So 80 years is still a fraction of that. And a compost would be even better because it needs kind of microorganisms to degrade, and it needs about 50 to 70 degrees for those microorganisms to live. And all of that you have an industry compost. So it would be really, really cool if we would have a possibility to collect PLA in a school and biodegrade it. Or the other option would be just to collect it and injection mold something or something with it, something useful, just reuse it for something useful. And that's something that I give you for yourself at home. Maybe you come up with a really good idea how to reuse all the stuff, all the wrong prints. Okay, why 3D printing? Why do I do it? I was working for a company as a 3D printing person, and we had a competition of 3D jewelry, and the things were extremely beautiful that we got, but not very printable. As you can see to the lower right, those objects are really, really, really thin and really hard to create. So I was thinking, okay, this needs improvement. So that's the reason why I'm doing my courses. But in general, the reason why people should or could do it is because it can foster problem-solving skills. It can reduce the fear of hard subjects such as mathematics because you implicitly use it anyway. You can create 3D printing objects that are completely personalized, so that completely fit your needs. It makes use of different media, so you go from 2D to 3D. And so that means you have a completely virtual idea and you can make an actual object out of it, something that never existed before. You came up with the idea. Through the multiple representations, you have multiple points of view on the topic. Usually it's a very fun experience to do it, also a very frustrating one. So if you overcome the frustrations, then you can get very creative. Therefore, through the entire thing and it being a process and connecting to so many different things like informatics or chemistry or physics or mathematics, it's a STEAM experience because you cannot do anything without actual thinking about how does it look like. And for example, for mathematics or education, you can create manipulatives or I don't know, objects you show around or models of something. And you do not have to rely on models in a book. So those models become actual 3D.
So
I use
to upload, but I don't know how to upload the PPT.
a bit louder. What?
Oh, just upload.
Was there a question? Anyway, so this is what I use it for. I have a really, really large lamp, 3D printed. Our vacuum cleaner did not fit under my furniture. So we added some feet under the furniture to have it a little bit higher. Then at the coffee machine actually can hold 0.5 kilogram of coffee beans, my coffee machine, but they come in 1 kilogram sacks. So I created kind of an extension so I can put in the entire bag of coffee beans in there. And this is a spoon created by my husband with the exact amount of sugar that he wants with his coffee. So it can be a very personalized object. We also asked some teachers what they believe could be the benefit for students. And of course, they were talking about motivation, because technologies are always a motivation for students to attend and to be observant, and it's new and it's fancy. And they said that the students also developed STEAM skills, which of course we thought was true because we found it in literature before that. Then they said that they had the possibility to apply their skills and learn new skills that they can apply. And what they also reported is within the teachers and within the students, communication was fostered. So between teachers, they started to talk to each other because, for example, I don't know, there was something in English and they asked an English teacher, what does that instruction really mean? Or there was something that was not working with the computer and they asked the informatics teacher, hey, can you help with this? And also the students started by doing problem solving. They started to communicate to each other. And basically that's what we thought. But what was new to us is the teachers also reported that the students avoided misconceptions through the use of multiple points of view on the object, like multiple media, having it in 2 dimensions and 3 dimensions, having them realize that something's really 3-dimensional, seeing connections and relations between the things. So having the possibility to actually not only physically, but also virtually rotate everything. The students started understanding relations. They started to see STEAM around them. So they started to see mathematics around them or physics around them or something. The teachers also said that they less need to explain why a skill or something that they teach them is important, because they apply it right away. And they started to consider STEAM careers when they didn't before, which is really, really, really cool, because that probably means if we go with our teaching more hands-on, then perhaps they will learn that their skills have value. It will be less abstract and they will consider STEAM careers. This is Ingo Witzke, and Ingo Witzke said 2018 with Hoffart that the benefits, according to him, for 3D printing in education are that you have lots of designed materials already, which I will show you afterwards, that is already usable. So you can just download and print and use it right away. But another option, of course, is creating individual materials for the students and from the students. They can create their own ideas. They can apply and use programs and technologies on the way. Also, it can train the spatial imagination, and self-direct learning is fostered because you have a problem and you work problem-oriented, and then you solve it and you have your benefits right away, which can increase motivation. Visualization of geometries, for example, in mathematics by Duval, is a process that requires a visualization, which in our case would be a 3D printing object, and the construction of it. So the construction, the 3D modeling and the 3D printing could be very closely connected. And the reasoning whether what you actually want, how you want to solve your problem, how you construct your object can really solve what you're doing. And this is what Diego says. Diego Lieban probably is known to some of you, and he's a colleague that was also at JKU, and he kind of exploded into ideas how to use 3D printing and in general digital technologies, digital manufacturing for schools. So in this picture, you can see a variety of different things. For example, on the top, you see how a cube can be disassembled and reassembled. And that can not only be done virtually, but also physically by downloading the objects from GeoGebra and 3D print them. On the right side, on the upper right side, you also see the same thing. So basically, division does not say how you need to divide an object or a cube. It can be, there's an infinite amount of how you can divide things by 2 or 3 or 4 or whatever, and have forms like that. So that can create lots and lots and lots of 3D printable puzzles. On the lower left side, You can see how spirals can interact. So it's perfect if you want tessellation, if you want to have nice tessellation somewhere, or you want to use this in your mathematics lessons or something, or want to learn about it. It's absolutely nice for that. It's gorgeous. And in the center, in the lower center, you see proofs of volumes, for example. You can prove by 3D printing that certain objects have the same volume, even though they look completely different. By, for example, pouring in salt, or flour, what he did in this case. So if you want to check out on GeoGebra, Diego Lieban, he has like a close to infinite number of ideas how to use 3D printing. And this is also what inspired us for games. So we also started creating games. Here in the GeoGebra book, you find how you can create games yourself with GeoGebra, and they can help you with problem-solving skills, to encourage students to just start their own thing and just solve their own problems. And it can be very motivational to use games. Sassy last week told you hopefully more about games. And if you're interested in that topic, Sassy is the woman to go, because she knows everything about it. Okay, from model to print. How do I get something like this? This was done from one of the teachers from the courses. So how do I get something like this? Usually first you get inspired by something. You have an idea, which can be really, really tricky. So that teachers reported that was sometimes the hardest step they had to overcome, creating something really meaningful. Then you start doodling and planning and developing a model. You 3D model it. You investigate and observe it using various technologies or virtually, whether it really fits your needs, and you slice it and you create it. And then usually you find, okay, that didn't do the trick, and then you have to remodel. What we have to keep in mind for 3D printing is that everything we have is not really a round shape. We always only have 3D triangles. So basically what we have is always something that is edgy. And if you want something really, 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 really round, then you probably run into problems. So always keep round shapes to a reasonable extent. And this is basically how 3D printing is working. So what the steps of 3D printing are. Whoops. First, you have some kind of a model. Then you come with a software called Slicer, which really slices it like bread into 2D slices. Then you create from that code that tells the machine what to do. And this code is kind of like creating a jigsaw puzzle of what you previously had. So it's more a one-directional thing. And then you tell the printer, okay, now go. The slicer is the absolute most important thing, and that's what I will show you in detail today also. Like I said, no, it makes a 2D model out of a 3D problem. That's the point of it. And it calculates the height and the material and the printing speed, and it can also sometimes repair your model if there's an error somewhere. And it very, very highly depends on your printer. So probably all the printers in Cecilia's bag have their own slicer settings, because it really, really depends on the nozzle diameter, how much material you can put through, about the layer height. The higher you get, the faster you can print. The building space. So how large a printer, you see that in the back, the printers have different sizes. So if you create a G-code for the really, really large printer with a large object, it will just not fit the other printers. So it's a very delicate thing. You cannot just create one G-code and print it anywhere. Yes, this is where Sassy is just going. So printing something in there can be much bigger than in other cases. And the jigsaw puzzle created G-code is basically just telling the printer printer's motors go upwards, start the fan, stop the fan, heat the nozzle to 200 degrees, now heat it to 205 degrees. I don't know, go forward one step, go backward one step. And on the lower right, you see what it basically looks like. It's just some letters and some numbers. And this is telling the machine what to do. Okay, now for the first exercise, or basically the main exercise here. I would like you all to download a software called Repetier Host, which I will give you in the chat. The picture that you see in the center, that is from Repetier Host, and it's a software that's free. And the benefit of the software is you can connect your printer and your computer directly. So it kind of makes use of lots of slicers. And all of the slicers have similar functionality, but they look completely different. Yeah. So I will quickly stop the presentation and show you my entire screen. So for example, this is what Repetier Host looks like, whereas this, for example, is what the Creality slicer looks like. So they kind of look very, very different. What you see on the left-hand side, you have things like layer height, shell thickness, I don't know, bottom and top thickness, and field density, and speed, and bed temperature, and those things. And these are things that you find here also, like this is the speed and the infill. Unfortunately, it's in German. This is the cooling. This is the layer height, so in which steps you have. This is the support structure. All of these things, so basically they have, and here you can switch the slicer if you want. So this has built-in lots of slicers that you can use. And you can see they also have a bit different settings here. And basically, this is a version of that, more or less, just with a different UI. So they have very similar functionality, but they all look a little bit different. And usually you can get a slicer software it usually comes with your 3D printer. So I'm going to keep going with the presentation now. And in 5 minutes, we're going to do this exercise after some more information. Because probably you wonder, okay, what's a 3D printable model look like? What would be a good model for 3D printing? There's tons of platforms to get 3D printing models from, but they are not always useful for 3D printing. Some are for games. So for example, you see down here, we have a dragon from Turbo Squid. Whereas here it says 3D Make, which already points towards that you can use those for 3D printing. And with dragons, I have a very tangent relation because I had to print one. And I will tell you the reason why 3D printing with dragons is really, really hard. Okay, what do we have here? That's a dragon, a 3D printed dragon. But what do we see? We see wings. We see they are very spread out. We see lots of details here. So like lots of scales and teeth and whatnot he has on his head. I don't know, like spikes. Yeah, and that thing already has some holes because 3D printing a wing is extremely hard. Just imagine a bat. How thick really is the wing of a bat? And if you have something that's delicate, is it thick enough to print? Because keep in mind, what we have is we have a nozzle of a diameter, I don't know, maybe like 1.4 millimeters. And that's it. So you cannot get smaller than that. We cannot go and just clock the nozzle with one of our fingers to have it smaller and thinner. And that's the actual problem that we are running into here. So that's a physics problem. It's a real life problem that we run into. So this is why I really recommend never to start with a dragon. That should be like the last thing you want to print. Scaling is a problem. If you have something that's thinner, then the nozzle can print. Then you run into the problem that you see here. If we had a dragon wing and the nozzle would be too large, what does the printer do? It does decide, should I print it, shouldn't I print it? That's what the slicer does. And the slicer then decides whether to print or not, but you really want a dragon wing. So sometimes you get objects that really don't work because it's just too small for your nozzle. And if you scale it a bit, then you see, oh, it's fine. It's a bit, and here you can already observe the printing time. Here we have like 24 minutes, a bit smaller, and here we have like, no, it's even less time. Interesting. So we just scaled it a tiny bit. So it could be printable. And you can see here, it's just one outline here. Printing time is the absolute killer thing. So which sizes are usually useful for a small printing time? You should keep to objects that are about this size. Like if you print something for the first time, it's nice to print something this size. You cannot really go larger than 15 by 15 centimeters reasonably, because the larger your object gets, the longer the print needs. And prints can go sideways. And if they go sideways, then you probably have a problem. So the longer print takes, the more sideways it goes. Now back to the slicer software. Did you download Repetier Host? If not, I will just show you, and you just can follow what we are doing. To avoid problems, you really think about the problems during the modeling stage. Later, when you have the 3D printer and you print it, it's too late. As you can see on the right side, it's probably art that you create, but it's very likely not the model yet that you want. You have to think about the technology, about the 3D printing technology. So should it be sustained? Should it be in education? Should it be easy to use? Should it be cheap? All of those things. Then you have to think about the orientation of your model. A model like this, you probably want to cut it into pieces and then glue together. Because what do we have if we have a 3D printer that we have right now? We need support structures that we otherwise have to remove. So we also have to think about spacing. How close together can we pack objects? If we pack objects together, because it's really warm, maybe they can melt together. You have to think about holes, where to put holes. Where can you save up on printing material? Because less printing material means less printing time. The supports we already discussed, and the cutting also we already discussed. And you have to think about multiple parts. What happens if you have multiple parts? Should they be printed together? Are they interlocking? Can you only print them together? How does all of that works? And all of these things you have to think about beforehand. So here we have our slicer settings. On the left-hand side, there's Tinkercad, where you can, for example, create a model and download it, and then you load it onto the Repetier host, for example. And you see that, I don't know, our object would take 21 minutes to print, in contrast to 23 minutes, because we just cut out the mouth, as you maybe see. And that already saved us a couple of minutes. Then we can think about where can we still optimize. So perhaps we do not need a handle for a cookie cutter that is that thick. Maybe we can just cut it away and make it less high. That saved a lot of time. Just cutting all of that thick material away and just leaving a very thin layer, reduced it to 13 minutes already. In other 3D printer, if you get for example, a Creality printer, you will have a large variety of printers to choose from, and you will have to be very, very careful which one to choose. So always make sure that you are choosing the correct printer. And please, very, very, very careful with the letters. Sometimes it happens that if you buy cheap products from China that are limited in their language skills, language possibilities, that they kind of offer Chinese as a first option. And if you are not able to read Chinese letters, it will be really hard to set back the language. So whenever you choose a printer and set up a 3D printer slicer, choose the model that you have, because like I explained before, the slicer is just connected to your printer model then and has all those presets, and choose a language that you understand. This is the machine settings that we also showed previously. So basically all the slicers have this. You just tell it which size, which height, which depth, what the nozzle is and everything. Then usually with whatever slicer you have, you can just add objects by dragging and dropping, which you could, if you wanted, with Repetier host also. So for example, this is the same object that we had previously in Repetier host, we have now in the Creality slicer in the latest version. I think it's the latest version. Sometimes they update it and then it still has the same functionality, but the buttons are completely somewhere else. That's a bit confusing sometimes. And then usually you have a large button that says slice, as you can see on the bottom. So when you do that, then the cutting starts. And before you do that, you can think about a lot of things. So that's the other Creality slicer version. How do you want it to stick? How's the orientation? As you can see here, maybe having it flipped upside down is not the best idea because it could knock over. How fast should you print it? So for example, Artisan, you have a variety of choices. So choose wisely. Always, after changing something, click that slice button because it will tell you how much time your print will take approximately. So you can just try around with the settings until the time that you see is somewhat near what you want. Then you rotate it to somewhat near what you want. So for example, this is 13 minutes, this is 5 minutes, just by rotating it. The more contact you have with your object to the ground, the safer it is to print also. Maybe it's also a good idea to look at your printer where's good spots, where's not so good spots. Sometimes printers are not completely even, and sometimes there's areas that work better and sometimes there's areas that work worse. Basically, the main settings that you have is the layer height, how much material in one step you print, the shell thickness, so how dense your object is, the infill, that's also a density thing, the temperature, which you should keep, as you can see in the center, about 200 degrees, more or less, the support that you need for this to float in the air, and the material flow. Sometimes you will find that your printer is creating strings of material, or it is not really enough material for one layer to really look good. So sometimes you have to go 110% of flow or 90% of flow, depending. Then you have advanced settings, such as the speed of the very different layers of the top layer or the bottom layer. Sometimes you want the bottom layer to be really slow to stick properly. And then you also might have, if you have a very expensive printer, you can have dual extrusion with 2 filaments, with 2 colors at the same time. Also, what's important is cooling. So usually you just switch it on or off, but you can also say, okay, if it's not sticking for the first round, maybe I just switch off the cooling, the fan, so it's still warmer, and then it probably sticks better. And these are things that you can do to improve your printing experience. Printing time optimization is what's really, really, really important. So rotating your object, scaling your object, how many layers you want, do you really want it that high? How fast do you want it? Maybe it's an ugly print and you just need to go a bit slower. Maybe it just did not stick to the ground. It just started moving somehow. And there's tons of problems that can go wrong. Like the power is suddenly gone, or the material is not going, the material flow is no more possible because sometimes the spools just jitter or nothing's moving. And then you need to stop your print and just check the problems and reprint it. So whatever you do, if you do 3D printing, first thing you should check is material coming out. Because if you have a print for 3 hours and you leave, and after 2 minutes, the material is no longer flowing, you have the machine in use for 2 hours, but you didn't print anything. Is everything hot enough? So it should be at least 180 degrees, the minimum at the nozzle. Is it sticking, or is it just not properly working? Does it smell really, really awful? Then you probably have a temperature problem also, or the filament, so the material got dirty and you should change it. And is the size okay? Did you want it in that size? Or do you need it larger or smaller? Because sometimes that can be really, really confusing because it's a virtual object. For repairing, sometimes it needs repairing. You can also do that in the Repetier host because it makes use of the internal repairing possibilities that Windows has. So this is some software I already showed you last time. That's just useful to adapt your model if you're not happy with it. And that's already basically the end, because it's 3 o'clock. And I will just show you, by dragging and dropping, I just show you how to reduce printing time. So what we have here by dragging and dropping, I just put on a cookie cutter. Then I go to slice. Usually there's a large slice button somewhere. And it will tell you, oops, nearly an hour. So what could we do? So it also tells you the layer height is 66 layers. What could we do? We go back.
We are watching your presentation, Eva.
Oh, sorry.
I don't know, maybe you changed the...
Wait. I will redo. Can you see it now?
Now it's okay. Thank you.
Okay. So here's the large slice button. And if we press this, it's slicing in slices. So actually we could go and check each layer. But it's really, really a long time it needs for a print. But do we really need it that large? Maybe half the size is good. Here we are at 15 minutes, which is already much better. But maybe we do not need it that high. So maybe if it's dough and we just roll it really thin, probably a little less high also works. Yeah, looks like we already have 11 minutes. And as you can see, we have one layer outwards, so we should not scale it much smaller. But everything is still as it should be. And if you're wondering about the blue thing around, that's something that most 3D printers have. To make sure that material is really coming out. Some slicers just add rounds and rounds and rounds and rounds, and before the print is starting. So you're seeing. Goodbye, Catherine. Sorry, I still forgot your. I will give you the paper at some time in the future, somewhere. So anyway, and when you're done, as you can see here, I have connected my 3D printer actually to this Repetier host that I have here. If you're done, you can also check by manually controlling the printer here what the printer should do. So for example, I could switch on the air vent or do the heating. So currently the heating is set to 210 degrees for PLA printing, for that special PLA that I have, and 60 degrees for the print bed. So it's about the glass temperature, so it's sticking. And if you're done with all of that, you probably, that's my kitchen and that's the 3D printer. Probably you have a 3D printer somewhere. Tables are always too short. This is a 3D printer that we created ourselves. So you cannot really buy it anymore, I guess. Basically, you can see all the necessary parts here. Here is the printed object. Here's the print bed on which we printed the object. And it's the cookie cutter we saw earlier. So this is about what you can print in 50 minutes. And here is your last lesson, very important lesson. 3D printing, and now it's a bad word, takes a shitload of time. So if you're screwing this because you didn't have a proper 3D printable object, you just wasted 1 hour of your life. And since we cannot get that hour back, better not. Better decide carefully what you want and carefully what you're 3D printing for. Okay, are there any questions? If you do not have any questions, you can always write emails to us and always ask and inquire other things. So if there's nothing else I can show you, I hope you're inspired now and you know that the first thing that you look for is the material coming out or not? Because if it's not, then not even like you're not getting a result. Okay.
Maybe they need to try the 3D
Yes.
printer before to have questions.
Yes. Unfortunately, 3D printing is really, really hard virtually. You have to try it yourself and you have to test yourself. That's why I gave you the Repetier host. You just drag and drop in, you try out different slicers, you try out the times, just check the different layers, check whether they still work, whether your object still works. That's always very, very important. And how long 3D printing takes, because that's the second most important information. First, material flow. Second, takes really, really long. Okay, there's much, much more information on the GeoGebra book and more explanations. Yeah, also the do's and don'ts and how to kind of avoid pitfalls. That's it.
Great. Thank you, Eva, very much. Some people is saying bye. So
Yes.
I can make a D model in GeoGebra, then save it a D
Yes,
model.
you can do that.
It's a technical question, Eva. Maybe you can answer.
Yes, you can. I can quickly show you how to do that. I just need to open GeoGebra. Can we, for example, search for a 3D model? I don't know, maybe this. Then we, unfortunately, no, that's just a video. It's not really an app. We need an app where that was created. Do we find an app? Here we have one of my apps for that. So this is the app actually. Then we go here, and since this is a game, we can just decide the form. So this is a 3D object, a truncated prism. We go download as. We say we want the 3D print. Then important, please check field solid, because otherwise you get tons of different things. Then we'll call this logifaces part. Export it and open it, for example, in Repetierhost. So this is the object that we have here. Here you can see that it's basically just consisting of triangles. So that's a really, really small file size for a very large object, because it's basically just triangles. Then we go to slicer. And probably we want to turn it a bit. So perhaps this is easier to print because it has more surface on the bottom.
Eva, please switch GeoGebra into this slicer.
Oh, sorry.
Sharing.
It's again the sharing problem. Thank you. Somewhat. It's not working really. Okay. Do you see it now?
Yes.
Okay. So basically, this is the object that we got from GeoGebra. Just let's try again. I will start this. Okay. To show you the entire process. So we have download as. We have 3D print. We say field solid. And we say it's one logifaces part. Here we have it, and we open it. Can you see it now?
Yes, perfectly. It's
Okay.
opening.
Sometimes
Perfect.
it seems I got not my screen, but one specific.
Yes.
Yeah, then probably it's nicer if we do not have it like this, but more on the side. Also not like this. So we have it nicely to the surface. So it's sticking better. Then we say slice in whatever slicer you use. And then we see, okay, this object would take 33 minutes. Then perhaps we would go back and we would have, no, there's just 1% infill, just 5 to 7% is recommended to have it good. So like it has it's not breaking easily, so it should have about 5% infill at least. And perhaps we want it smaller though. So 24 minutes, that looks better. And there you would have it. So that would be an object directly from GeoGebra. And then you would just, on the left side, I just put out the plug from the 3D printer because the cable was not long enough. But you could just then print it. Here's a button print. Usually you put it on a USB drive, which is explained on the GeoGebra book. Usually you would put it on a USB drive or something, and then you would start the print on the printer and not connect it directly. I'm just doing this because it's a homebrew. We made it ourselves, 3D printer. Okay. Anything else I can make you happy with or provide info?
Okay. I think there is no more questions in the chat.
Okay.
So maybe they need to try.
May I would like to ask Eva or
Yes.
to explain how we can set the fill, because it can also help us to make a printing process less long.
What do you mean?
When you set the fill, you can
Which
change the 3D solid, how it is filled.
Oh, yeah, that's not changing the printing time really. It just means if you make it a solid, then you're just downloading the object from GeoGebra and not the surroundings. Usually, if you're in GeoGebra, you have things like the coordinate system or something. And if you do not tell GeoGebra that you want the solid that's in there, but all the surroundings, then you get everything. And that's looking a bit different. So I can show you not in that. I switched off the coordinate system, so I cannot show you in that applet really. Maybe I can show you in that. No, that's not it. That's it. So if you add the coordinate system back in and some planes and stuff, GeoGebra has the possibility to give all of this a thickness in contrast to many other software. So if we do not say field solid, then you see here we have a thickness. And this thickness is given to all the objects. So let's call it this 2. I hope you can see Repetierhost again now. Is it working?
Yes.
Okay, that's good. As you can see, I switched on the plane and it also gave the plane a thickness. I switched on the coordinate system and here you see a really large arrow and another arrow. And also you see a really large orange warning here, because if you do that, sometimes GeoGebra is putting things into things and it has to be repaired first. That can be done, for example, here. It sometimes takes a while. Now it's repaired and now you see it's full of triangles. But basically, this is the problem. So in the center, you still see what we had before. So this truncated prism is still in the center, but it's surrounded by the coordinate system and the planes and everything. So this is the difference when you're saying field solid versus giving it a thickness, because it means you give everything a thickness. You can even see that was the edge of the, so like, whoops, these edges, this is what we can, here it's a sharp edge, whereas here it looks like this was the objects that were creating this. And this is the difference.
Can I ask something?
10 things.
The first object, the right one you showed, will the printer print it like hollow, or will it be completely filled inside?
Ah, okay. So that's something that was not made clear. I will show you. It depends on your printer settings, not on the object. So if we have, this is really hard to see, so it kind of burns in my eyes. But if we see this object here, we already have it sliced. We can go through it layer by layer. And we see the first layer, it's a closed layer. The second is still a closed layer. Then we will turn it a bit to see it better. Then after a while, it is open. So inside is more or less hollow. This is a setting that you put in here. So this 6%, this infill density of 6% is basically what we have here. If I go here and make it more dense, like, I don't know, more than 20 really isn't needed. Do you see that's the infill changed? So it's much more lines now inside. And if I go here and tell it to be completely full and slice it again, then you see that every layer is a full layer. But of course, more material printed and more distance traveled means more time. So if we go back to, I don't know, 6% or something, it should be a bit faster when it's not that dense and filled inside. Is this answering your question?
Yes, thank you.
Okay. Anything else?
No, in the chat, at least.
Now that we collected your souls, we're happy.
Okay, well, if we don't have more questions, thank you, Eva, very much for the presentation
You're welcome.
and for the materials that we are sharing by here in the chat, but then when we upload the videos for YouTube, we will add all the presentation and links and everything there. And we will send by email all of you, so everything's okay, I think so. Okay, thank you everyone to be here during the 4th session webinars, and maybe next time we are presenting more interesting things, so you can follow us by Facebook and other social medias. Thank you very much. Bye bye.
Thank you. Goodbye. Thank you, Ceci.
Goodbye. Thank you, Eva.